Hi, my name is Shankara Pailoor, and I'll be presenting automated policy synthesis for a system called Sandboxes. This is joint work with Xinyu Wang, Hovav Shacham, and Isil Dillig. Sandboxing is a widely used technique for mitigating many types of attacks. This is because normally, applications run with nearly unrestricted access to all system resources. A sandbox restricts the application to only use resources it needs to function correctly. That way, if an attacker hijacks control of the application, they have a limited surface area to attack. So system call whitelisting, or Syscall Whitelisting for short, is a very effective kind of sandbox. Each sandbox is a policy written in a DSL that specifies which syscall usage patterns are required by the application in order to function correctly. So a usage pattern just refers to a syscall and its argument values. At runtime, the sandbox will only allow the application to invoke usage patterns specified by the policy, and any policy which is not allowed is blocked. This technique is effective because after an attacker takes over an application, they will typically compromise the rest of the system by using syscall patterns that are different from the applications. To make things more concrete, I will present a common attack scenario where system call whitelisting is useful. Here we have an attacker that wants to take over many machines. They know that there's this popular PDF viewer that has an exploitable bug which allows them to execute arbitrary code. As such, the attacker creates this malicious PDF and tricks a large number of users into opening it. So this PDF will do two things. First, it will trigger the bug in the PDF viewer, but it will also execute code designed to gain control of the machine. And this code will do so by executing some sequence of system calls. So let's say, for example, this code executes an open followed by an ioctl and a write. And after executing this code, the attackers manage to take over, let's say, the operating system. So let's see how system call whitelisting could prevent this attack. So when the developer creates this PDF viewer application, they will also write a policy in a DSL for a specific sandboxing framework. And this sandboxing framework will be typically tied to some operating system. So in this example, the policy specified by the developer, let's say, allows open and ioctl, but it only allows ioctl if the second argument is equal to 1. So now let's say at runtime, the PDF viewer opens this malicious PDF, and the attacker code starts to execute. So the sandboxing framework will intercept the open call and allows it to execute because it matches the policy. However, the attacker's ioctl call does not match the policy as the second argument in the attacker code is not equal to 1. As such, the framework will block this call and thus the attack. Now, while system call whitelisting is very effective, in practice it's actually very rarely used. This is because programmers don't typically know all the system calls that are needed by the application to function correctly. This is because most system calls are kind of invoked in third-party libraries like libc, which are fairly opaque to programmers. As such, it's very easy for programmers to write policies that terminate legitimate executions. Moreover, even if they do capture the required usage patterns, they still need to write a policy in a DSL, and these policy languages vary greatly in terms of syntax. For example, there are many policy languages like seccomp-bpf, pledge, AppArmor, SE Linux that are all quite different from each other. So our goal is to automatically generate these syscall whitelisting policies. So to do this, we developed a tool called Abhaya, which takes as input an unsandboxed application along with a policy DSL and generates a whitelisting policy. Abhaya has a few nice properties. First, it generates sound policies in that they never block a syscall usage pattern that is needed by the application to function correctly. Second, Abhaya's use policies are precise in that they constrain the syscall usage pattern as much as possible. And finally, Abhaya is general in that it can generate policies for multiple policy languages. So Abhaya's workflow consists of two phases. The first is a static analysis phase, which we refer to as Syscall Analysis. And it takes as input this unsandboxed application and produces a Syscall invariant. And this invariant is a formula that overapproximates the application's Syscall usage. In particular, all the models of this formula are going to correspond to allowed usage patterns. So this invariant is going to be the specification for the next phase, the optimal synthesis procedure, which also takes as input a DSL and synthesizes the most restrictive whitelisting policy in that DSL that overapproximates the invariant. So at this point, you might wonder why we actually generate a policy that overapproximates the syscall usage of the application, since an overapproximation can seem insecure. And so there are three main reasons. So first, computing the exact syscall usage is undecidable, so any analysis must either over-approximate or under-approximate the usage. Second, under-approximations can actually block required syscall usage patterns, and for many developers and companies we've talked to, this is an unacceptable cost. In fact, Chromium has this feature which allows end users to disable the sandbox if it blocks legitimate syscall patterns, and this fundamentally undermines the usefulness of the sandbox. And finally, most policy DSLs are actually designed to over-approximate the syscall usage. So there may not actually be a good policy which under-approximates the application's behavior. So with this in mind, we decided to synthesize policies that over-approximate the application's behavior. I will illustrate Abhaya's workflow with an aid of a motivating example. So we will use Abhaya to synthesize a pledge whitelisting policy for the Unix utility cat. And the source code for cat is shown on the left. It just reads a file and prints its contents to the screen. Since our goal is to synthesize a pledge policy, I will briefly describe what a pledge policy is. So pledge is OpenBSD's Syscall Whitelisting framework, and a pledge policy is just a list of groups where each group allows a set of syscall usage patterns. A syscall is allowed by the policy if only if it is allowed by at least one of the groups. The more groups a policy has, the more permissive the policy is. Pledge has 35 total groups, but this table only shows the 4 most relevant. So stdio allows all syscalls required to print and read things from standard IO. rpath allows syscalls that produce read-only effects on the file system. And then wpath and cpath allow writing to and creating files respectively. So the desired policy in this case is stdio and rpath. And in the rest of my talk, we'll show how Abhaya actually synthesizes this policy. So the rest of the technical part of my talk will consist of we'll describe the 3 main components of Abhaya's workflow. So performing the static analysis, computing a Syscall invariant, and finally synthesizing an optimal policy in the target DSL. And I will start by describing the key design decisions behind our static analysis. So there are 3 observations that motivated the design of our static analysis. First, we observed that most syscalls are invoked in complex libraries like libc. For example, the cat application doesn't directly invoke any system calls, but instead calls the libc functions putchar, getc, and fopen. As such, in order for the tool to be useful, the analysis should be able to precisely analyze those libraries and also be scalable. So to maintain precision when analyzing these libraries, we used an interprocedural analysis, but in order to be scalable, we used procedure summaries to avoid reanalyzing functions in similar contexts. Our second observation is that the values of syscall arguments typically depend on several program variables. So in order to compute a precise over-approximation of the syscall usage, we need to compute an over-approximation of the whole program. So if we look at the implementation of fopen, one of the library functions invoked by cat, it calls open at line 14. So the second argument of open depends on most of the local variables of the function, along with the mode argument. More generally, we found that 80% of program variables affect at least one of the syscall argument value. So with this in mind, we based our analysis on abstract interpretation to compute an invariant over the whole program, and then translate that invariant to do a formula over just the syscalls and argument values called by the application. Finally, we found that in order to constrain important syscall argument values, we needed a precise abstract domain. For example, in general, it is important to restrict the second argument of open as much as possible, since it controls the permissions of the files, so like reading, writing, and executing. But if this argument value is left unrestricted, then the attacker has much more freedom in how they affect the file system, potentially ransomwaring all files. However, in this fopen example, the value of the second argument depends on the contents of the mode array and the variables m and o, whose values differ along different execution paths. As such, our abstract domain should be able to reason about the contents of arrays and maintain some precision across different execution paths. While this domain needs to be precise, we also found that it doesn't need to be relational, since system call argument values typically don't depend on other system call argument values. As such, the abstract domain used in our analysis is a reduced product of this array expansion domain and the disjunctive interval domain. Our static analysis computes invariants for the whole program, which over-approximates the concrete executions of the application. Now I'll describe how we convert those invariants into a formula over syscalls and argument values, which we call a Syscall invariant. So after running our abstract interpreter, we get an invariant at each program point. Now for each system call site, we encode the program invariant at that point into a formula over the system call and its argument values. For example, the program we compute at line 14 at fopen for the cat application is shown on the right, along with its corresponding formula below. The idea is that the formula is going to over-approximate all usage patterns produced by the application at this particular call site. So now our syscall invariant phi is just the disjunction of all formulas we compute at every call site. In other words, every required usage pattern is going to be a model for one of these disjuncts. So for the cat application, Abhaya returns the following invariant. Now the syscall usage pattern on the left is not a model for phi because of the second argument value, whereas the pattern on the right is a model and corresponds to an invocation from fopen. So the last phase of Abhaya's workflow synthesizes an optimal policy in the target DSL. But before describing our optimal synthesis procedure, I would like to briefly go over why we perform optimal synthesis. So first, the syscall invariant we compute cannot always be directly translated into a program in the target DSL. So second, we also want to find a policy that is sound in that it over-approximates the syscall usage of the application. The only way we can guarantee it's going to be sound is by over-approximating the syscall invariant. However, not all sound policies are desirable because most are far too permissive. So in our work, we decided to find a policy that's the tightest over-approximation of the syscall invariant that can also be expressed as a policy in the DSL. So going back to our workflow, the optimal synthesis procedure takes this invariant as input along with the policy DSL and generates a whitelisting policy in that DSL. Although most policy languages are quite different syntactically, they actually have very similar semantics. As such, we designed a framework-agnostic language that captured the semantics of multiple sandboxing DSLs and synthesized policies in this language. After synthesis, we perform syntax-directed translation to produce the equivalent policy in the framework-specific language. Now, the subpolicies produced by this phase are sound, in that every model of the syscall invariant is actually going to be a usage pattern that's allowed by the synthesized policy. It's also optimal in that there's no stricter policy in the DSL that's also sound. So now our synthesis procedure consists of two core components. First, we perform enumerative search over sketches, where each sketch is a policy with some unknown constants. Next, we developed a novel variant of CGIS, which tries to find an optimal completion of each sketch. In particular, we use an SMT solver to generate blocking clauses to prune both suboptimal completions as well as unsound completions. And at the end of the synthesis procedure, Abhaya returns an optimal policy. We now briefly show how Abhaya synthesizes the desired policy for the cat application. So given this invariant computed from the analysis phase, Abhaya performs top-down enumeration of policy sketches. So for each policy, we check whether it's sound and optimal. So here are some policies that Abhaya enumerates during synthesis. So in particular, Abhaya identifies psi1 as unsound, and so it discards it. The second policy, psi2, is actually sound, but it's in fact suboptimal. Now psi3 is sound and more restrictive than all other sound policies, so Abhaya marks it as optimal. Eventually, after enumerating all policies, Abhaya returns psi3 as the strictest policy in the language. We now evaluated Abhaya by answering the following three research questions. Can Abhaya synthesized policies stop real-world attacks? How do Abhaya's policies compare against manually written ones? And finally, how efficient is Abhaya? So we used Abhaya to generate pledge and seccomp PPF policies for 674 applications. In particular, we generated seccomp policies for 491 Linux applications and pledge policies for 183 OpenBSD ones. Seccomp is the default sandboxing framework for Linux, whereas pledge is the out-of-the-box sandboxing framework for OpenBSD. To evaluate whether Abhaya could block real-world exploits, similar in pattern to the OpenE attack scenario, we gathered all privilege escalation exploits for Linux in the last 4 years. The idea is that each privilege escalation exploit could be used by the attacker to compromise the system. Now, we only gathered Linux, exploits for Linux and not OpenBSD, because there were no reported published exploits for OpenBSD attacks. Now, for each Linux application, we synthesized a seccomp policy and counted how many exploits the policy would block. So the key takeaway here is that over 90% of Abhaya synthesized policies could actually block all the privilege escalation attacks. And this showed that Abhaya synthesized policies are actually quite useful in practice. Next, we compared the Abhaya synthesized policies with developer written ones. And ideally, we would have compared against both manually written seccomp and pledge policies, but among the 491 Linux applications, only 4 had developer handwritten seccomp policies. However, all 183 OpenBSD applications came with pledge policies. So for each OpenBSD application, we synthesized a pledge policy and measured the F1 score of each policy, where the developer written policy was taken to be the ground truth. So we found that 60% of Abhaya synthesized policies exactly matched the developer written ones, and the average F1 score was about 0.9. To determine whether Abhaya was scalable, we measured the runtime of our Syscall analysis and policy synthesis phases. The average size of each application we analyzed was around 122,000 lines of LLVM bitcode, including the library dependencies. Our analysis took about 7.3 minutes on average, and our policy synthesis phase took about 2.3 minutes. As such, Abhaya is able to synthesize both useful and precise policies for large programs in a timely fashion. So in conclusion, we introduced the policy synthesis problem for Syscall sandboxes. We presented a precise, scalable analysis for computing Syscall invariants. We also described a new optimal synthesis algorithm for generating whitelisting policies and showed that Abhaya's policies are both useful at blocking attacks and are competitive with handwritten ones. Now I'd be happy to take any questions.